Welcome back. This is week 9 of inverse methods and heat transfer. In this video, we'll be looking at our first classification algorithm. This is called Logistic Regression model. This will be done in two parts, this video and the next video. The task that we will be trying to do is what is known as binary classification. Okay, so the list of topics that I'll be covering within this video is what is binary classification? Why is it important in practice? Where could we see something of that sort in, let's say, heat transfer scenarios? And then I'll give you a couple of examples to set up what we'll be doing in the next video. The first is a one feature example. Remember when we had linear regression, we called whatever went into the input as a feature. So for example, you could have x, x square, etc. as features, or x1, x2 as features when we looked at linear models. But similarly, we'll look at a simple, just to start with, what is a one feature example of logistic regression. And there you will see the sigmoid function that I introduced you to in the last video arises naturally. Okay. Next, we will move on to a two feature example, and we will talk about something called the classification boundary, which is an important concept within binary classification. Now, recollect that every machine learning algorithm that we will be discussing is basically a combination of four things. How we represent the data, what is the forward model, what is the loss function, and what is the optimization algorithm used. Okay. And these two is what we will be covering in this video. Okay. So we'll simply be covering the how we represent cases, data in case of classification problems, and what the forward model is. And the loss function and the optimization algorithm we'll be covering in the next video, and then I'll summarize the net situation. We'll do the same thing for our categorical or multi-class case as well. So let's now step into the data representation and data set portion of binary classification and talk about what it actually is. So what is binary classification? So binary classification is simply splitting or categorizing or classifying, of course, something, whatever it is. It could be an image, it could be a field, into two possibilities, or into two, what we call them, classes, which is why it's called classification. Okay. So for example, of course, the standard example I have been giving throughout, when you have an email, you can say spam or not a spam. Or if you have an image, you could say cat or dog. You could say cancer, no cancer. Or thermally safe or thermally unsafe. Okay, so stuff like this. So we have just two classes in which we wish to split it. Okay. Now, how do we represent data in such a case? Now, you do nothing special for the input. Okay, so for example, you have an image, just like we discussed last week, you represent it by pixels and unroll it, etc. If you have an email, of course, there are many special techniques to work with text. Or if you have simply a flow field or a temperature field, you represent it with numbers as usual. So this for data representation is both for X and for Y. So this is as usual. Okay, whatever the input is, it stays as usual. Now Y, on the other hand, you can, as it turns out, you can do it in two different ways. Okay, so we are going to take the first very, very simple sort of method to use this. We will say 0 or 1. So Y is basically a binary. Remember, Y is the ground truth. So I could have a case like this. Let's say we are looking at the design of a thermal chip, and what you have as X is, let's say, power input. So let's say you have a chip, and you have a whole on your mobile, and a whole bunch of apps are running. And as the number of apps increases, obviously the chip gets heated up because the power input is high. And here is the response, that is, does this chip fail or not? So let's say we have a lot of measurements that we make as we are going about it while doing testing. So during testing of this chip, you collect a data set. So let's say I'm just making some numbers up. Okay, so 100 watts or something is the power which is input. This is safe. 110, this is safe. So let's say I have decided 0 means safe and 1 means unsafe or fails. Okay, something happens, something burns up. Similarly, 115, it's safe, and 120, it starts failing. And 122, it fails again, and 130, it fails. Okay, so let's say we collected this data. Now, what you want, of course, is when you give a new power input, okay, something like 112, is it safe or not? So this would be a classification task. You can think of it similar to, let's say, measuring sizes of tumors. This is, of course, very simple and very simplified more accurately. Obviously, no real case will be just this one-on-one. This is what I said as a one-feature example. Usually, you'll have multiple features. I'll give you an example of this later on in this video. Okay, so this is a one-feature example. Now, why is ground truth what you saw? So if we draw this in a graph, just like we were doing the linear regression cases. Okay, so let's say I plot these points and I have 100, 110, 115, 120. These are not really evenly spaced, 122 and 130, something of that sort. I could say that Y as a plot looks like this, that at these points, it was safe. So let me draw this with a green circle when it is safe. So safe, safe, safe. So this was 100, 110, 115. And this is 120, 122, 130. And this was unsafe here. So I'll draw this with a red cross. So this is 0, 0, 0. And at this point, I have 1. Now, our modeling task is to find out Y hat which will fit this data. Okay. In that sense, this is like a regression task, which is why it is called logistic regression model. Okay. You will see this in some detail just shortly. How should I fit? So the question really is, how should I fit some curve here which will fit these data points? So now the simplest solution, so let me just draw a solution, for example, is something of this sort. Okay, so this could be a Y hat. And indeed, in the earlier days of machine learning, this was the Y hat that was chosen, a step function. This turns out, due to multiple reasons, especially for optimization, this is not ideal. Okay, so we will actually not use this model. We will not use a step function model because it's non-ideal for what we wish to do. Now, you can think of a few other models, but I'll not confuse you with those at this point. But you can think of a natural model. A natural model could be a smooth function that goes from 0 here to 1 here. Okay. So this could be Y hat. And this Y hat is a smoothed step function. So Y hat has the following properties. Y hat of minus infinity is 0. I am obviously writing it with some mathematical abuse here, I'll make it a little bit more precise, of plus infinity will reach 1, and it is smooth in the middle. So this is the general idea of a function. Obviously, we need it to switch somewhere in between 115 and 120. Okay, so that is where we want to see this rise, and I'll tell you how to do this in 2 steps. Okay, so the idea is we create a new function which is a smooth step, and that's called the sigmoid. And the sigmoid is written as sigmoid of some variable z is 1 by 1 plus e to the power minus z. So this is called the sigmoid function. It has the following properties. First property is as z tends to minus infinity, sigmoid of z, you can see, is e to the power plus infinity, so which is effectively tends to infinity. So 1 by infinity, this tends to 0. Second property, as z tends to plus infinity, sigmoid of z becomes exponential minus infinity, which is approximately it's tending to 0. So 1 by 1, this tends to 1. Okay, so instead of writing equal to, tends to 1. Okay. Third is when z equal to 0. Okay, when z is exactly equal to 0, this basically becomes, you can check, e power 0 is 1, 1 by 1 plus 1. So this becomes sigmoid of z is 0.5. Okay. So let's draw that now. So sigmoid of z looks something of this sort. As z tends to minus infinity, it tends to 0. So tending to minus infinity, tending to plus infinity. Let's say this is z, and this is sigmoid of z. Somewhere in the middle, it will actually hit at 0. This will hit 0.5. Okay. Now, before I go back to our original problem and explain this a little bit further, we have z here, whereas x there. How do we translate between x and z? You can immediately notice a few things, that the sigmoid becomes flat as z tends to plus infinity, and sigmoid tends to flat when it becomes minus infinity. The slope here, we will calculate that it is not as bad as what I have made it to look, but it has infinite number of derivatives, so we can easily take derivatives of it. Okay. Now, how do we use this here for our model? Okay. So I'm going to mix two things. One is how we are going to actually interpret this, and second thing is how we are going to actually implement this. So how we are going to interpret this is as follows. We will say that my y hat need not be exactly 0 or 1, but it could take values in the middle. Now notice this, our original data set was y, because I am now measuring what actually happened in reality. What actually happened in reality was this chip either did not fail or it failed. Whereas when I'm making a guess for what will happen for a new chip that is given to me, I can only assign probabilities. What I can say is, if the power is really small, obviously my probability of failure becomes smaller and smaller. It gets closer and closer to 0. Similarly, if the power is really high, you're dumping a lot of power on it, then the probability of failure becomes higher and higher. So the first thing we are going to do as far as interpretation is concerned is, instead of saying y hat represents failure or success, y hat represents probability of failure. So when probability of failure is really high, it means y hat gets closer to 1. When probability of failure is really low, y hat gets close to 0. Another way of saying it is y hat is probability is that y is equal to 1 for a given chip power input. Okay, so don't worry too much about the notation here. I'll not dump you with too much complex notation, but at the very least, I hope you can agree that probability of failure is the same as saying probability that y equal to 1. Okay. Now, the next thing is this, a key point that happens where the situation flips. So let's say the probability of failure y hat turns out to be 0.6. You say, well, probability of failure is 0.6. Then people will assume that it is more than 50% chance, so it has failed. So after this step of giving a probability, if you still have to make a choice about whether it is 0 or 1, right of this line, where y hat is exactly 0.5, you will assume that it is more probable to fail. And left of this line, you will assume that this is safe. So this line here, this critical line, is called the classification line. One side of the line, you have one outcome. Other side of the line, you have other outcome, at least in terms of how you predict. So how do we find this line? Well, we look back here. Where do we want that line? We want that line at when sigmoid hits exactly 0.5. But remember, we can do that reverse calculation. Sigmoid of z is 0.5 when z equal to 0. Okay. So when z equal to 0, sigmoid equal to 0.5. So z equal to 0 is the classification boundary or classification line. This is true both in one feature, two feature, or in multiple features, as we will see shortly. So z equal to 0 is the classification line. Fine. But what I have here on the x-axis is x. It's not z. So how do I set that? Now notice, let us say arbitrarily, I say that this boundary should happen at 117. Okay. So I will say something like when x equal to 117, z is equal to 0. Now you might be wondering, how exactly am I going to build this model? Okay, do I have to do this by hand? The answer is no. We will see further details in the next video on how we actually end up building this model. But when x equal to 117, z equal to 0, so you can kind of set z is x minus 117. So this satisfies all our properties. Now notice when I do z is x minus 117, when I come here, the value becomes z equal to minus 7. Here the value is z equal to 0. Here the value equal to z is 13. Now what happens at z equal to minus 7? 1 by 1 plus e to the power plus 7. Okay. E power 7 is a reasonably sized number. Will be approximately, so 2 cube is 10. So this will be around 100. So 1 by 101. So the probability that this is a failure becomes approximately 1%. Similarly, when you come here, the probability that this is a success might become something like 99%. So which tells you that in case you define z as x minus 117, this would work. Now, in general, we do a very clever thing. We say z is for one variable w0 plus w1x. Now, this should immediately start looking a lot like our linear model. Okay. And we say y hat is sigmoid of z. Okay. So notice this. You first do a linear transformation on x. Next, you do a non-linear activation. This twofold stepping, okay, first taking a linear step and then taking a non-linear step, I'll show this pictorially also shortly, is what makes the forward model. Okay. But why are we defining the forward model this way? Again, let me explain it using the same example. See, in general, when you have only one variable, you will always have this situation. You have something like this, and you have some critical point. Let's call this X critical, where you want to make this jump between a failure and a success. So you could have something like this: failure, 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 success. Now, Z is, like I said, W0 plus W1X. Now, in this case, in our example here, you can see W1 is 1 and W0 is minus 117. Okay. So when you set W1 is 1 and W0 equal to minus 17, you immediately get Z equal to 0 means X equal to 117. This is X critical. But 2-3 things could happen. One, I have drawn it in a way where, of course, for the chip example, it means when power is increased, probability of failure increases. But you could have definitely a case where higher numbers are better, and you could have an opposite direction thing. So which is why you might actually require sign flip. So you might require W0 minus X. So in that case, whenever Z crosses W 0.5 or whenever Z crosses 0, it goes in the opposite direction. The second thing that W1 controls is, imagine a case where I write Z equal to X minus 1, but I make it 2X minus 1. Okay. So when I do that, I will get sigmoid of Z such that this slope is a whole lot sharper. So when we keep a sigmoid, it is very smooth and it transitions slowly from failure to success. As you increase the slope, as you increase W1, you are looking at sharper and sharper transitions. Okay. So this controls the slope of change, and this controls usually the location of transition. Put together, our model is like this. Our model is, let me draw this in a figure, and you'll see in some sense it's easier to interpret in a figure. We do the same thing that we did with the linear model, 1 multiplied by W0, X multiplied by W1. You sum the two, and let's call this output Z. You don't stop here. You put our sigmoid function on top of it. And what comes out here is G of Z equal to Y hat. So let's say this is a function G, which in our case was sigmoid. So look at the pipeline. The pipeline is X comes in. Let's say the power, you multiply this by some weight, multiply 1 by some weight, add the two, get a value, run it through the sigmoid function, and here you get probability of class 1. Okay, whatever class 1 is. In case what goes in here as X is an image, then maybe class 1 is a cat. Then what goes in is an image, comes here, put a sigmoid, it will give you, is this image a cat or a dog? So that's the simple example of how you build a forward model with just a single variable. Now, this, of course, is the pictorial or the graphical representation of the model. Here is the algebraic model. Algebraic model I have already written, but let me write it out explicitly. Our algebraic model is Y hat equal to sigmoid of, which is 1 by 1 plus e to the power minus W0 plus W1x. Okay. So this then is our forward model for single feature logistic regression. This is called the logistic regression model. Now, how do we learn W0 and W1? Can I go? Now, of course, once I give you W0 and W1, you can draw this picture. Okay, and you can do a classification. But can I find out W0 and W1 given this data? That is, given some engineer is measuring some thermal data in a chip, and he wants to find out, okay, what is the critical temperature or what is the critical power at which this chip starts failing? Now you can immediately see this is given the effect, you are trying to find out the cause. So this is an inverse problem. And we will see how to solve this inverse problem in the next video when we talk about the loss function, etc. Okay. Now, all this is, of course, for a single feature. Now, what we will move on to next is multiple features. So let's see that one. The same ideas that we used for just doing the single feature case, we can now think about multiple features. So what do I mean by multiple features? When we give the data set, we have these cases where the input, whatever it is, whether it's an image, if it's an image, it would require a lot of input. So taking back my favorite 60 cross 60 image, this would require 3600 image or pixel information in order to give one input. Let's take a simpler case where we have only two inputs. Okay, so let's call this the first data point has just two inputs. Okay, or two inputs, or the input is a 2 cross 1 vector. The ground truth again always remains either 0 or 1, and then you have y hat. So what could be an example of this? So let me take a non-thermal example just for some simplicity here. So let's say we are collecting these patients, or we are finding out data for these patients who are coming to a doctor, and these patients come with a temperature and with some cough. Okay, and we measure this. So patient one, let's say, comes there with some reasonably high temperature, but the cough frequency, the frequency with which this person coughs is kind of low. Patient two comes and this person again has just two features. You are just measuring these two. This person has slightly lower temperature, but this person's cough frequency is high. So let's say we keep on collecting things like this. Lots of people here and lots of people here. Something of this one. I'm just making something up. Okay. And a new person comes. So let's say after doing all this, we track these patients and find out whether they have COVID or not. And this is basically the data set. Obviously, this is not a realistic data set. In realistic COVID, we would collect a whole lot more information rather than this. We would have X-rays and whatnot. But let's say, again, I'm taking a simple case. So something of that sort. And you just label these people as saying, okay, person one came. This guy had some temperature, some body temperature, and some cough frequency. And you know what? This person didn't have COVID. Person two came, had some other temperature, some other cough frequency, but this person did have COVID. And similarly, you could create, let's say, this entire database. Let's say we have again 100 patients, 0, 1, 1, 0, 0, etc., etc. So this is our database, and we collect that. Now, the classification question is, if a new patient comes, can you tell me whether this person has COVID or not? Now, please understand, I mean, we should not get lost fully in machine learning. We are still doing an inverse methods course. Please understand how this is an inverse problem. The inverse problem is like this. If you tell me, okay, patient one has COVID, patient two has COVID, can you does not have COVID, etc. Can you find out the parameters in your model? That's the inverse problem. What parameters or what underlying cause would have led to this effect? Now we are mathematizing that and making it into a data rather than a physics model here. I mean, we really don't know the mechanism. In fact, it's not causative. It's a correlation that we are looking at. It's not as if cough and temperature caused COVID, but it is just that these parameters are implicit data-based causes that we are looking for. Okay. Now, coming back to this, notice that in this case, we can think of a line here, which I'm going to call the classification line. This is very much like the classification line I drew here, right at the beginning. On one side of it, we had all the failure cases, and another side of it, we had all the safe cases. So similarly, coming back here, on one side of it, we have all, let's say, the no COVID cases. And another side of it, we had all COVID cases. Okay, high temperature, high cough, COVID. Low temperature, low cough, no COVID. Okay, but high temperature, but low cough, no COVID. Something of that sort. So we have a line. Obviously, the real, in case we made a COVID case of this sort, it would not sequester or classify so neatly. It will look a little bit more complex, which I'll talk about shortly. Assuming this is somewhat of a realistic example, let's proceed further. Okay, now this somehow is basically going to turn out to be the equivalent of our z equal to 0 line. But how are we going to achieve it? Simply extending whatever we did till now. So I am going to first start pictorially, unlike last time, because it's actually the more natural way to go. So I have 1, I have x1, I have x2 as input. I'm going to do exactly the same thing blindly, assuming this is somehow going to magically work, and it does. I will just take W0, W1, W2. Interestingly enough, the earliest models of neural networks were exactly like this. In fact, they were physical models used exactly for classifications. We do this, and we know we want an output which is again either 0 or 1. Okay. And again, we will run this through a sigmoid. And what comes out as output basically will give us the probability of COVID or not. You'll say, okay, how is this going to magically work out? Nothing. We don't really care that it works out somehow exactly. There is no physics here. All we are doing is, okay, I was given 3 numbers or 2 numbers, x1 and x2. I need to give an output that is going to be between 0 and 1. Then how will it figure out COVID or not? That's where the magic lies in our optimization routine and the loss function that we will give, which we will give the next video. But all we are doing right now is simply setting a forward model. Please understand this fact. It's a key fact. All we are doing is blindly setting a forward model which will somehow satisfy our data representation. What is our data representation? That I should input the temperature, I should input the cough frequency. My output data representation said that it should look like a number which is 0 or 1. We modified it a little bit and said, I'll give a number between 0 and 1, and that's it. Okay, our modeling is done. This will look ridiculous, but it tends to work. Okay, so I'll talk more about this sort of disturbing situation when we come to neural networks, that we almost give nothing and still we get fairly good outputs. So we have simply satisfied mathematical constraints having nothing to do with COVID, saying, I am only looking at a probability, so it should be a number between 0 and 1. And how does this look? This looks like this. It looks like this, that the output here, let's say, is Z, and Z is what goes in here. So Z is W0 plus W1 X1 plus W2 X2. This Z I'm going to call as usual as the linear activation. Okay, or a linear combination or a linear portion of the neuron. Okay. Now, usually when you see a neuron in neural network, as you will see, both these are put together, and it's assumed that both the linear combination and the nonlinearity happen one after the other. Then I will say A, just to say activation, is G of Z, which is basically sigmoid of Z. And Z is a scalar, so you do sigmoid of Z, and then you say Y hat is the same as A. So this is the sequence of steps we follow for the forward model. Give me a temperature, give me a cough frequency, give me W0, W1, W2, combine these, then just run them through a sigmoid and I will get a probability. How do I find out that, ensure that it satisfies this data set? That's where the inverse problem kicks in. And you look at this data set, and we have to set an objective function, which we'll look at in the next video. And you adjust it so that Y hat works for all the cases that we have given the data set for. Okay, if I write it explicitly, this is what it will look like. Notice Y hat is simply a scalar, because all we are demanding out of this network is not multiple numbers, but a single number, which tells you how probable is COVID or not. So what it is 1 plus e power minus, or sorry, minus W0 minus W1 x1 minus W2 x2. Notice y hat is simply some function of x1, x2. Notice this. In this figure, it's not so obvious that it's a function, but regardless of how many things I put in the middle, y hat is always a function of the input with some intermediate calculations going on. All right. What about the classification line? So what about the classification line? So the classification line is the line z equal to 0. Why is it the line z equal to 0? Because at z equal to 0, y hat will be exactly 0.5. How come? Y hat was sigmoid of z, and when z is equal to 0, y hat obviously is sigmoid of 0, which is exactly 0.5. So one side of the line you will have one class, because when z is less than 0, this means y hat will be less than 0.5. And when z is greater than 0, y hat is greater than 0.5. Let's look at what this model is doing. What is it actually doing? I'll tell you a graphical interpretation also. But all it is doing is trying to find out these parameters, which will somehow turn our input into a line, the line z equal to 0. If you happen to fall on one side of the line, it will say no COVID. If you happen to fall out on the other side of the line, it will say COVID. Now you might say, how is it doing that? Think about how we are doing it. We are doing this visually. All the algorithm is doing it algebraically. Why? Because as you will see shortly, z actually means perpendicular distance from this line. Okay. If it happens to be negative, it falls on one side. If it happens to be positive, it falls on another side. The genius really of the algorithm, which we will see in the next video, is to find out this line. But this is no different from finding out the regression line, which balances the data points. So all it is doing is finding out a balance between the data points. And the further you go here, the more the probability that you have COVID. The further you go down here, the more the probability that you don't have COVID. Okay. So let me show you why this is so. So z equal to 0 means W0 plus W1 x1 plus W2 x2 equal to 0. This, of course, is the equation of a line in 2D. Why so? It might become clearer if I label these somewhat differently. Suppose I call the C plus AX1 plus BX2 equal to 0. Or I call this AX1 plus BX2 equal to C or minus C. Or I call this X2 equal to minus C by B plus or minus A by B x1, which is the same as saying y equal to mx plus some other constant C. So this is a line. Similarly, Z in general is W0 plus W1 x1 plus W2 x2. Now you might have to brush up your 2D analytical geometry to remember this, that this essentially is the perpendicular distance. So suppose I look at this points x1 and x2 and I want this distance, that will exactly be Z. W0 plus W1 x1 plus W2 x2 will give this. So if it is positive, it lies on one side. If it's negative, it lies on another side. Notice what happens as Z increases. Okay. As Z increases on one side, this means that perpendicular distance increases. If perpendicular distance increases, it means more and more certain. Okay. In case this is not obvious, let's look at the 1D case, which is why I started with the 1D case. When you're right here, you're only about 0.5 sure that whether this will fail or not. As you go further and further here, sigmoid of Z becomes closer and closer to 1. And that makes sense, because the further you move away from this boundary, then more and more the power is increasing, and that's telling you that, oh, I'm more and more likely to fail. Similarly, further and further you move into this boundary, the more and more the power decreases, and the more and more certain you are that this is just completely safe. So these two put together basically tell you the interpretation of Z. Okay? So Z basically tells you which side of the classification line you are lying on, and also how far you are. So if you are exactly on the boundary, then you are at Z equal to 0. And this is basically how binary classification works. By somehow magically figuring out what this optimal line is, the classification optimal line. Notice, once again, the line is optimal in some sense, just like it was in regression. So both in regression as well as in classification, we have somehow magically landed up on this line, okay, which needs to be optimal in some sense. But optimal in what sense? What is the loss function that I can give that will tell me that I am well balanced? So that goes back to the initial question that I was raising. What is the loss function? And what is the optimization algorithm that will ensure that I come somewhere in the middle? So that we will see in the next video. In this video, we saw that the data representation basically should be represented as 0 or 1 as far as y is concerned. It should be between 0 and 1 as far as y hat is concerned. And that the forward model simply is sigmoid of z, where z is some w1x1 plus w2x2, etc. But in the next video, we will see how we will land up at W0 and W1 and solve the inverse problem. So I will see you in the next video. Thank you.